All right, so let's define what enthalpy is. So enthalpy is heat, and so it has the symbol H, and it is the heat gained or lost by a reaction system at a constant pressure. And so that's always a little caveat that's put in there. When you start doing pressure changes on a system, you're doing work, and work has the ability to transfer heat or change temperatures of situations. And so all of these are going to be done at constant pressure. Now, the other thing we need to do is we need to define the term system and surroundings. So if we kind of just draw a big circle here, and we'll call this the universe. All right, so that's everything. So in the universe, we can specify here's a particular system that we're talking about. The system could be a chemical reaction. It could be a reaction flask. It's something that we're going to set aside to focus on. Everything in the universe that's not in the system is classified as the surroundings. And then all of these heat transfer problems, we're doing it from the point of view of the system. Is the system gaining heat, or is the system losing heat? And so again, depending on how you phrase the problem, you can kind of say, well, from the surroundings point of view, yeah, that's true, but we always kind of focus on what is the system, what are we defining as the system, and is the heat coming or going? Now, enthalpy, H, absolute enthalpy, unless you have a completely isolated system where it's not in contact with the surroundings, which is an impossible thing, we can't really measure the absolute enthalpy of a system. The best we can do is measure the change in enthalpy, the delta H. And so you're always going to see the enthalpy term here with the delta in front of it. I can't just look at a chemical reaction or a thing and say, oh, the absolute enthalpy is this. You just can't do that. So we measure the change in enthalpy, which is the final enthalpy minus the initial, and that's going to be our delta H. You're also going to see the term Q here, and Q is just another symbol for heat. It's the heat gained or lost by a system. And the P just refers to it being at constant pressure. So that's the important thing. Now, in terms of the signs of enthalpy, if there is a heat transfer from the system to the surroundings, the delta H is going to be negative. It's going to be less than 0, and that's going to be exothermic, or the heat is going out of the system. If we're talking about a heat transfer from the surroundings to the system, all right, heat is going into it, and the delta H is going to be positive. So we have an endothermic process. Right? All right, so let's talk about calorimetry or heat transfer problems here. We're going to go through conceptually with a graph like this, and then we're going to do a problem that's going to involve these different segments, and we're going to be measuring the type of heat here. So we're looking at the addition of heat to a system of ice, and it's going to eventually go to water and ultimately to steam. And so we're tracking that addition of heat down here along the x-axis, and we're going to have the temperature along the y-axis. And we're going to look at each of these segments in turn here. So down here at point A, this is going to represent ice. Right? Now, let's say that ice is even at negative 25 degrees C. It doesn't matter where it is, right? But if I start adding heat into this, right, from the segment from A to B, all right, up here, heat is going to be added from point A to point B to raise the temperature of the ice up into 0 degrees C. Right? And so as I'm adding heat, you'll see that the temperature is also rising. So let's say it's at negative 25, negative 20, 15, negative 10, until it gets to here to point B, And so now I have ice that is at 0 degrees Celsius, right? And so that's going to be my addition of heat. Now here is the key thing. If you don't remember anything else from today, here is an absolute rule. You cannot have a temperature change and a phase change at the same time. You can only do one process or the other. You're not going to do them both at the same time. So once we get here to point B, I have ice that is at 0 degrees C. And that's important because at 0 degrees C, that's the melting point of the ice. So from B to C, the temperature is going to remain the same. It's going to remain at 0 degrees Celsius. Right? So if I put that 0 out here and notice that I've got a flat line, all the heat that I'm adding, right? So we're still adding heat. We're going from left to right, but all the heat is going into melting the ice. So here is from A to B a temperature change, and from B to C, we have a phase change. And so all along that time, I'm going to have a mixture of ice and water. So by the time I get to point C, I have water and the temperature is at 0 degrees C. So everything that goes along here, all the heat goes into adding or causing the phase change. I don't have some water that's going to absorb some heat and get up to 2 degrees C while I still have some ice. All the heat goes into melting that ice. Now, once we get to point C, I've got all liquid. And at this point, as we continue to add more heat, the temperature can start to rise again. And so the temperature is going to keep going up as I add heat until I get to point D. And point D is going to represent 100 degrees C. Why is that important? Well, that's the boiling point of water. You're not going to get water at 1 atmosphere pressure any higher than 100 degrees C. Right, so at 100 degrees C, any heat going in is now going to contribute to the phase change. So we have 100 degrees C water. And then at point E, we're going to have 100 degrees C steam. Right. But all along this time, all that heat is going into converting the liquid water into steam. There is no temperature change here. Now, once we get to point E, there is no liquid left. All we have left is steam. And so any additional heat is going to go into changing the temperature of that steam. And so again, each of these segments where you have a slope going up, those represent temperature changes. And where you have the flat lines here, those are going to represent phase changes. You can only have one or the other at a particular time. You can't have them both happening at the same time. All right. And so this is got a lot of practical importance here. Right? If I want to cook some pasta, right? So I put water on to boil, and I turn my gas stove, all the way up to 11. I mean, I've got all the heat that I can put into that is going into that water. Well, the water is not going to get any hotter than 100 degrees. So once it reaches the boiling point, I can't get it any hotter than that. Now, again, the higher up I turn my stove, the faster it's going to get there. But just turning up the stove more is not going to make your water hotter. 100 degrees is the maximum temperature you can get the water. And so if I'm cooking pasta, that means if I put the pasta in there, in about 7 minutes or so, you'll get that pasta fully cooked. If I want to cook that pasta faster, I need to get that temperature up higher. And the only way to do that is if I increase the boiling point of the water. And so to do that, I'd have to increase the pressure by putting it in a pressure cooker. Now, for a pressure cooker, cooking pasta is impractical because there's time it takes to get the pressure up. And so by the time you do all that, you might get it hotter, but you're not going to save yourself any time. But if you want to cook some other things, if you want to cook some beans, right, instead of boiling them at 100 degrees all day, you can put them in a pressure cooker, increase the temperature, and you can cook them faster. Also, this is where pressure canning comes in. If you wanted to can some certain items, you have to get that temperature above 100 degrees C. If you don't, you're not going to kill all the bacteria, and you run the risk of getting botulism poisoning. So you got to be very careful. There's some items that you can with boiling water, and there's some items that you have to pressure can. And it all has to do with this idea, I can't get boiling water any hotter than 100 degrees C. All right, now as we do these calorimetry problems, we're going to have two equations. All right, one is going to be for temperature changes, the other one is going to be for phase changes. Right, so we've got two processes going on here. We've got temperature changes that are the slopes, and then we have phase changes, which are the flat lines. So let's go over what these two equations are. All right, for temperature changes, you have Q equals mc delta T. All right, so this is the first one that you're going to have to know. And again, you shouldn't have to memorize it, because if you're doing what you need to be doing, you're going to be doing lots and lots of these problems. And so Q equals mc delta T will just roll right off your tongue. All right, Q is heat, just another way to say enthalpy. M here is going to be the mass of your substance that's changing temperature. So M is mass. All right, C is the specific heat capacity. The specific heat capacity is a constant that's inherent to a substance, and it's the heat required to raise the temperature of 1 gram of that substance by 1 degree C or 1 Kelvin. Now, does it matter whether you're in degree C or in Kelvin? Well, in most of these, we're talking about the change in temperature. And a degree C and a Kelvin are the same size. So even though the scales are different, if I go up 1 degree C or go up 1 Kelvin, I've changed in the same amount of temperature. So degree C and Kelvin are interchangeable so long as we're talking about a change in temperature. Right? And so you'll notice that the problems are going to flip back and forth between doing degree C and Kelvin. You just got to watch and make sure you're not on an absolute temperature scale, but you're talking about the changes in temperature. Now, there's a variable in this. Sometimes you'll see temperature changes as Q equals nc delta T. And the big difference is, instead of having mass, we've got moles. And so the C value that you're given is the molar heat capacity, which is the heat required to raise the temperature of 1 mole of a substance by 1 degree C or 1 Kelvin. By far, the mc delta T form is more common, and you're going to see units of C that have grams degree C rather than moles degree C, but you always got to keep a lookout for it. All right, now the third version of this equation, it's going to take the amount of the substance, either the mass or the moles, and the specific heat capacity, little c, and it combines these two terms into a big C. And big C is referred to just as heat capacity, not specific heat capacity. Or if you're doing a problem where a substance is burned in a calorimeter, those are quite common, big C is your calorimeter constant. So you'll see a problem have to give you what C is, or if you're told the heat and the change in temperature, you calculate C. So big C is heat capacity, little c is specific heat capacity.